Hello and welcome to today's lesson looking at terminal velocity. Now in today's lesson, which forms part of the GCSE Combined Science for AQA in the forces module, we're going to try to describe the forces on fallen objects. So in today's lesson, we're going to try and name the forces on fallen objects, relate how objects fall to forces that act on them and how they change during a fallen object's journey, and then look at how we can deduce instantaneous acceleration and velocities from motion graphs. So this links into the following part of the AQA GCSE Combined Science specification. It links into the acceleration part of the topic, which we've looked at previously in other lessons, but we're also in today's lesson going to really focus on the bottom part of the specification, that an object falling through a fluid initially accelerates due to the force of gravity, but then eventually the resultant force will be zero and the object will move at its terminal velocity. So we're going to take the concepts of acceleration and the velocity time graph and apply it to a particular situation. Now that's important because we can use a velocity time graph to work out if an object is accelerating by looking at the gradient of the graph, and this can then allow you to determine if an object has a resultant force acting upon it. So let's consider this particular velocity time graph. You've got a straight line section and you've got a flat line section. So the straight line section has a constant gradient and the flat line section has no gradient, a zero gradient. Now the gradient of a velocity time graph is the acceleration of the object. So what that means is if it's a straight line going upwards, you will have constant acceleration. Whilst if you've got a flat line, you've got no acceleration. Now again, only a resultant force acting on an object can cause an object to accelerate. So because in that straight line section, you've got constant acceleration, you must have a constant resultant force acting upon that object. Whilst on the flat line section, if there's no gradient, there's no acceleration, so there's no resultant force. Now we can consider the velocity time graph for any journey. But there's one specific journey that you must know the velocity time graph of, and that is of a fallen object. Because an object falling through a fluid, which is a liquid or a gas, so an object falling through water or an object falling through the air, initially accelerates due to the force of gravity, but eventually the resultant force acting on that object will equal zero, and the object will move at a constant velocity. Now we call that particular constant velocity a terminal velocity for a fallen object, and we're going to investigate this concept now. So for an object to accelerate, to change either the speed or change direction, because to accelerate is to change velocity, and velocity is a speed and a direction, it must experience a resultant force. Now when an object falls for long enough, the air resistance acting against the motion equals the weight acting towards the earth. This means that there's no resultant forces, as the two forces cancel each other out. The object does not accelerate, it stays at the same speed and the same direction because there's no resultant force acting on it, so it achieves terminal velocity. So there are three stages to any fallen object's journey. Now when an object first falls, there are two forces on that object, and there's two forces throughout this particular journey, and that is the weight, which acts towards the center of the earth, which in most situations is downwards, and you've got air resistance, which acts against motion. Now when an object first falls, the weight is larger than the air resistance, so there's a resultant force downwards, so the object will accelerate downwards, because a resultant force causes an acceleration in the direction of the resultant force, which is Newton's first law of motion. So the object accelerates downwards as there's a resultant force acting downwards, so the object will speed up going down. So what we know at this point is we've got a weight acting downwards, and we've got a smaller air resistance acting against motion. So as a result, there's a difference between these two forces acting on the object, so we have a resultant force. Now, at this part of the journey, we can show this on a velocity time graph. So on the velocity time graph, we've got a straight line with a constant positive gradient, which indicates constant acceleration. But in stage 2, as the object increases in velocity when it accelerates, the air resistance increases because more air particles are being pushed out of the way by the object every second. So the air resistance has increased, so this decreases the resultant force on the object, this decreases the acceleration. So now you'll notice that whilst the weight has stayed the same size, the air resistance has increased. So now the difference, the resultant force, is now smaller. So the object is still accelerating, but it's accelerating at a slower rate because there's a smaller resultant force. Because the resultant force and the acceleration it causes for an object are directly proportional for an object with the constant mass, which is Newton's second law of motion, F equals ma. So F and A are directly proportional when m is constant. So because the resultant force has decreased, the acceleration it has produced decreases. Now, don't forget to talk about this stage in a fallen object's journey. People tend to forget about stage 2 when they discuss this in a longer answer for an examination. So we can show stage 2 with the following part of a velocity time graph. So it's got a curving line curving downwards. So the idea is the gradient of the line is decreasing, so the acceleration is decreasing. But just remember, look on the graph, the velocity is still increasing because the line is still going upwards. It's just increasing at a slower rate. Now in stage 3, eventually the air resistance increases and increases and increases and increases until it's the same size as the weight. So now there's no resultant force acting on the object, so there's no acceleration on the object. The velocity stays the same for the object. You've achieved terminal velocity. So now the weight and the air resistance acting against the motion are the same size, so there's no resultant force, so the object is not accelerating. Now when there's no resultant force on an object, there's no acceleration, so it maintains the same speed with the same direction. So if the object is already moving, like it always will be in a fallen object because it's falling, it will keep moving, it will keep falling. So we call this concept inertia, and this again is Newton's first law of motion. So we can show this particular idea on a velocity time graph with a flat line, because this flat line has a gradient of 0, so it has no acceleration. So it has a constant velocity, which isn't 0 because it would be on the bottom axis if that was the case, on the x-axis if it was 0. It has reached terminal velocity. So you can see on a velocity time graph when a fallen object has reached terminal velocity because it will have a flat line which is not on the x-axis. So at this point, remember, in our journey, the weight has stayed constant throughout the journey because the object's mass and therefore the weight that it will have acted on it due to gravity has stayed constant in the journey. Now you might say, surely as it gets closer to the Earth is the strength of gravity not stronger? Well, it is ever so slightly, and the effect is so minuscule it can't really be observed on a human level, so we just say the weight is constant. It is the air resistance that changes size at different parts of the journey. So the reason why stage 1, stage 2 and stage 3 occur is because the air resistance force is changing on the object, whilst the weight force on the object is constant throughout. So let's just clarify what's going on. When an object first falls, weight is larger than air resistance. There's a resultant force downwards, so the object accelerates downwards. Stage 2, but as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second, so decreases the resultant force and its acceleration until eventually the air resistance has increased to be the same size as the weight, so the velocity of the object stays the same. The object has no resultant force acting on it, so there's no acceleration. It has reached terminal velocity. So that is a very, very important concept to understand. So let's just summarize what we've learned so far. The velocity is a speed in a given direction. Acceleration is a change in velocity per second, and it's measured in meters per second or meters per second squared. The average acceleration of an object is the change in velocity divided by the time taken, where deceleration is the change in velocity every second when an object slows down. The acceleration of an object can be calculated from the gradient of velocity time graph, and you can also calculate the distance travelled by an object from the area under a velocity time graph. And then finally, an object falling through a fluid initially accelerates due to the force of gravity, but then eventually the resultant force will be 0 and the object will move at its terminal velocity. And the terminal velocity is the constant speed of a fallen object when it's been fallen for a prolonged period of time, because it takes time for those stages to occur. And the terminal velocity occurs when the air resistance acting against the motion and the weight acting downwards are an equal size, and it's the air resistance that is varying throughout the journey, not the weight. So if you've learned in today's lesson, we can state the names of the forces on fallen objects, relate the objects falling to the forces that act on them and how they change through the fallen object's journey, and finally look at how we can deduce the different sections of the fallen object's journey from a velocity time graph. Thank you very, very much for listening to today's lesson. I hope you've enjoyed this lesson looking at terminal velocity and its link into acceleration and velocity time graphs. And in upcoming lessons, we'll look to see how we can measure terminal velocity by experimental methods. Thank you very, very much, and I hope you have a lovely day.